So this is the problem that we left off last class. So they're going to want us to basically find the percent unionized form of the codeine. So what we're going to do is we're going to utilize the buffer equation right here, and then we're going to plug in the pH as well as the pKa that they give us right here. And then once we subtract both sides by 7.9 and then take the anti-log of both sides seen right here, we're going to get the ratio of the unionized and the ionized form of the of that base. And so it's going to be 0.0398 to 1. And so to find the percent unionized, we're going to get the ionized over the we're going to get the unionized over the unionized plus the ionized and multiply all that by 100, and it's going to give us 3.82%. Okay, so remember that it's kind of hard to tell if a drug is acidic or basic by looking at the pKa, so we have to look at the functional groups to tell whether or not a drug is acidic or basic. So if we know two drugs are weakly acidic, kind of like the first two right here, then the one with the lower pKa would be more acidic, and for bases, the one with the higher pKa would be the stronger base. So ionization is what decides the water solubility of a particular substance. The more something exists in its ionized state, right here, the more water soluble it's going to be. But that same substance is going to have poor absorption through the placenta and the GI tract and other membranes. But at the same time, it's going to have good elimination by the kidneys because the kidneys eliminate water. And then for the unionized substance, it's going to be lipid soluble, so it's going to have good absorption through the placenta and the GI tract and membranes, but it's going to have poor elimination by the kidneys. So right here in a pH of urine, which is 6 in this example, the second drug right here, it has the lower pKa, so it's going to be the more acidic drug, and this means that it will ionize more in solution. And remember that when a drug ionizes, the more water soluble it will be, and it's going to have less absorption through the membranes. So drug 2 will also be more soluble in urine and be eliminated by the kidneys, while the first drug, this one right here, is going to be less soluble in urine and more likely to crystallize in the kidneys because they're not going to be eliminated like drug 2 is going to be. Now if we change the pH of urine to 8, then drug 1 would actually become more water soluble since it will ionize more at higher pHs. So right here, they're asking us to find the percent ionization of aspirin. So I already worked it out right over here. If you just subtract the pH by the pKa, you're going to get -2, and taking the anti-log of -2 is going to get you the ratio of the ionized over the unionized, and so it's going to be 0.01. That means that it's going to be there's not going to be very much ionized form of this drug, so it's going to be a lot more lipophilic. So that means that it will absorb into the membranes as well as the GI tract faster. Okay, so for this one, it's wanting us to get the percentage of the drug that will cross the placenta. Remember that the drug that passes through the membrane is going to be unionized, and so what we're going to do is we're going to take the anti-log of the pH minus the pKa, and then that's going to give us the ratio of unionized over the ionized form of the base. That's going to be 0.398, and then to find the percent ionized, that should be percent unionized, I'm sorry. It's just going to be the unionized over unionized plus the ionized times 100, and so that's going to be 28.4% of the unionized drug passing through the placenta. So buffers shield the solution and make sure that it doesn't fluctuate. So when the pH is equal to pKa, that means that the unionized and the ionized forms of that drug equal 50% each. And the same thing for basic drugs. So for acidic drugs, if the pH is greater than the pKa, that means that more than 50% is in the ionized form. And for basic drugs, if the pH is greater than the pKa, then less than 50% is in the ionized form. And we can check our work by going back to that clicker question. So do you see how the pH was higher? The pH was lower than the pKa, and so the percent ionized is going to be lower than 50%. Yeah, that's right. Okay, so buffers shield the solution and make sure that it doesn't fluctuate. So what would be in a buffer to make it resist change? So an acid and a base, basically. A buffer has to contain an acid and a base for it to resist the fluctuations in pH. So basically, when you add an acid like this, then the base that was already in the solution is going to buffer it out. And then same thing with a base. If you add a base, and the acid that previously existed is going to make sure that the solution isn't going to fluctuate. Okay. So strong acids and strong bases do not make good buffers when you combine them together. It's going to be the weak acid and strong bases, or weak bases and strong acids, that make good buffers. So the reason why weak acids and strong bases make good buffers is because if we had a weak acid like this, like acetic acid, and then we had a strong base like sodium hydroxide, the acetic acid would partially dissociate, while the sodium hydroxide will completely dissociate. The free hydroxide ions are going to combine with the free hydrogen ions that dissociated, as well as the acetic acid, and that's going to make water and acetate. So if an acid was added to the solution, then it would react with the free acetate ions, and then same thing for a base. If a base was added, it would either react with the free hydrogens or the free acetate ions. So in this clicker question, B is going to be the better buffer because it has a pretty similar amount of the unionized to the ionized form of the acid, of the weak acid. And then for this clicker question, A is going to be the better buffer because even though they have the same ratio of unionized to ionized form of the acid, A has a higher concentration of both, and so it's going to have the higher buffering capacity. Right, so for this one, it's wanting you to find the pH of the buffer solution, and so we're going to be using the buffer equation, this thing right here. But first we're going to convert Ka into pKa by taking the negative log of it, getting 4.74, and then plugging in all those numbers. We're going to get the pH is equal to 4.82, and this means that it's a good buffer because, as you can see, the pH barely changed at all from 4.74 to 4.82 with the addition of the sodium. Yeah. Okay, so for this problem, so for the non-buffered solution at a pH of 7, if we added 0.01 moles of strong base, the solution is going to have a hydroxide concentration of 0.01, and so taking the negative log of that, we're going to get 2, and then to get the pH, we're going to get 12. So basically, adding just 0.01 moles of strong base to a non-buffered solution is going to cause the pH to jump from 7 all the way to 12. So if we look at a buffered solution right here, at a pH of 4.82, adding 0.01 moles of strong base, what's going to happen is, so we're going to get we have the unionized form of an acid here, and then plus a hydroxide, and then here is the ionized form of the of the acetic acid. So if we basically do this little chart here, so originally we started off with 0.09, and that's just from this equation right here. We're going to start off with 0.09 of the unionized, and then we have 0.11 of the ionized form of that acid. We're going to be adding 0.01 concentration of the hydroxide, and so after we do all of that, we're going to subtract these sides by 0.01 and then add 0.01 to this side, and then this is going to be the final concentration of the unionized, the hydroxide, and then the ionized. And so if you plug it back into the buffer equation with 4.74 we got from the last clicker question that we did, multiplying it all out, we're going to get the new pH is 4.92, and so basically the pH didn't really change much. It went from 4.82 to 4.92, so this is a pretty good buffer solution. Right, looks like that is all. See you guys next time.